Modern rocketry was basically born in Europe, so it's no surprise that Europe has done some incredible things in aerospace, operating some world-class missions and building some of the most iconic launch vehicles. However, to date, the only real player in the orbital launch industry to hail from Europe has been Arianespace, a fairly traditional aerospace company. But that's all about to change. There's a resurgence of new space companies racing to be one of Europe's next launch providers. And as exciting as it is, it does make me question, how are these new companies going to compete with not only the traditional aerospace industry, but also the extremely competitive new space launch industry from all around the world? So today we're going to talk to two companies from right here in Europe, Rocket Factory Augsburg, or RFA, who, as the name implies, hails from Augsburg, Germany, and we'll also visit ISAR Aerospace from Munich, Germany as well. We're going to try and figure out, what are they doing different? How are they building these rockets? What's unique about their systems? Where are they going to launch them, and how are they going to launch them from Europe? And we're going to see how are they going to fit in this competitive marketplace. Let's get started.
3, 2, 1, That's one small step for man. Contact with a test 1.
Okay, this video is going to be a little bit different. Since we had the opportunity to visit both Rocket Factory Augsburg and ISAR Aerospace, I thought it'd be interesting to compare them to see how they're similar and how they're different. Come to find out, we couldn't have found two companies that are taking on the challenge of building and operating a rocket more differently, which is super fun. So what we'll do is we're gonna go back and forth between these two companies and compare and contrast their rockets, their designs, and their philosophies. But first, here's a quick overview of each rocket so you know what we're looking at during these tours. RFA is building a rocket called RFA-1. RFA-1 stands 30 meters tall and 2 meters wide, built out of cost-effective stainless steel tanks. The booster has 9 helix engines that are oxygen-rich staged combustion, running on RP-1 and liquid oxygen, otherwise known as Kerlox, with 100 kilonewtons of thrust each. The second stage has a single vacuum-optimized helix engine and has a small orbital transfer vehicle as a third stage too, called Redshift. The rocket is capable of an impressive 1,300 kilograms to sun-synchronous orbit and will launch from the Saxford spaceport in Scotland's Shetland Islands. ISAR is building a rocket called Spectrum, which is 28 meters tall and 2 meters wide, built out of lightweight, fully carbon composite tanks. The booster has 9 Aquila engines that are open cycle, running on liquid oxygen and liquid propane, or Propalox, which I don't know if that's a word, but it is now. And the second stage has a single vacuum optimized Aquila engine. Spectrum is capable of 700 kilograms to SSO and will launch from the Andøya spaceport in Norway, as well as the Guiana Space Center in French Guiana. And just for a quick side-by-side reference, here's how these rockets compare to Firefly's Alpha from the United States. They're all quite large small-sat launchers and will be competing for similar payloads. Now, we don't necessarily have reliable price figures for a lot of these rockets, so we can't really do like a good dollar to kilogram ratio or anything, but one thing we do know is there'll likely be some European agencies and companies who will be happy to fly on a European rocket. I should also mention quick that there are a handful of other launchers from Europe getting close to launching as well, but we'll just be focusing on these two today. Okay, now let me introduce you to Dr. Stefan Brieschank from RFA, who will take me somewhere I actually have never been before, inside a rocket.
Okay. Are you good? That was good. That was much better than...
First interview from inside of a rocket. Oh, this is crazy.
That is. Yeah, the really cool thing, if you look around, is that you won't see any large CNC machine parts. This is all a sheet metal construction. This entire stage is based on sheet metal. We don't have these typical Y cords that you typically find between the dome and the cylinder. They are very large CNC machines, super accurate parts that really drive up the cost significantly. And this is really a stage that is purely sheet metal work, so it's super, super low cost.
And so how do you guys determine how thick to make everything, and how did you get to stainless steel, and how do you make all these decisions? Because it's like one little thing changes everything, and it seems very overwhelming.
What we basically did in the beginning is we created a kind of artificial intelligence. We basically coupled 3 optimizers. The first optimizer optimizes the trajectory, like the best way how to get into space, into orbit with the least amount of fuel. Then we have a second optimizer that basically can read all of that and decide on all the structural designs. That basically it's a design code that says, okay, the wall thickness has to be this and that if the loads, if the bending moments and fluxes are this from the trajectory. And then very cool, we have a third tool, and this is our most important tool, a large cost database where the optimizer can go in and ask, hey, look, I've designed something, I made it from composite, how expensive is it? And the database says, look, you have chosen this geometry, it will be this cost. And that's really key, because now we could basically ask the optimizer, look, what is the cheapest way for the customer? And that's when this code designed the vehicle against to what we wanted. I did not want to have a stainless tank that looks cheap, right? I wanted to identify myself with a really slick, beautiful composite stage.
Right.
But we had no way of getting out of there because the cost of this construction, this is a very special kind of stainless construction because it's super low cost. A first stage costs less than a single engine. And we couldn't get out of this. The optimizer basically found this local minimum in this large cost database where you have the brewery tank.
Like a beer tank.
Like a beer tank. It's basically, it's very specific because it's a tank that is made with a wall thickness between 1 to 2 millimeters. For me personally, I wanted to make a really slick, beautiful composite stage. It hurt me personally when this optimizer that I started to really hate always chose the stainless steel construction. But the difference is very simple. A composite stage like this costs almost $500,000 US, and a stainless steel construction of this type is 10 times cheaper. And this is something you can't take out of the equation anymore. The optimizer always runs into this local minimum, and I can't ignore it. And it's quite interesting if you look at this in a traditional sense. You realize traditional rockets are built extremely accurately. Good example, Ariane 5, Ariane 6 features a 5.4 meters diameter, and the concentricity requirement is like here. We are 2 meters in diameter and we only require a concentricity of roughly an inch. So orders of magnitudes worse. The reason why that was done traditionally is because they didn't have GPS while the rocket was flying into space. And that's why they basically wanted to keep the rocket as cylindrical as possible to make sure that the disturbances through the atmosphere can be calculated. And this is one of the game-changing things now. We installed GPS or Galileo in Europe, and now the rocket can be basically built in a really inaccurate fashion, almost like a little banana shape.
It'll just compensate for it.
It will just compensate for it, right? We don't care. And that's this is a good example how humans have put up a system in space which actually allows us now to make getting to space cheaper and easier, more efficient. And we fully use that. If you read through a lot of requirements on traditional launch vehicles, they still have these very, very tight accuracy requirements in the spec sheets. And it's actually quite difficult to understand why, but we went through all of these requirements and we cut out everything that didn't make sense. And this is a very cylindrical tank for you, for your eye, but in reality, it's a design that is based on sheet metal only, and this keeps the cost down and therefore makes it really attractive to the customer.
Wow.
What you see here is very cool. These are all the flow-form domes, and one of the key challenges for us was to embrace this sheet metal construction. We basically had to make sure that we can flow form these domes as quickly as possible to make them cost effective. One of these domes is only a couple of grand, and it's made within just a couple of hours. The problem is it's not very accurate, and if you basically make 10 of those domes, you find they all have a different diameter. And we approached the entire stage construction in a similar fashion to how ball bearing manufacturers manufacture bearings. They make 1 million balls, and then they find 6 that are exactly the same size, and they can make 1 accurate bearing. We do the same. We make a whole bunch of these domes, and we just sort through them, and we will find 3 domes that are perfectly the same size, and we can make a stage.
Okay, I think this is the perfect opportunity to bounce over to ISAR Aerospace, where I met up with their VP of production, Bjorn Dressler, to see how they're manufacturing their tanks, which is almost the exact opposite of everything that Stefan just said.
This is
was built up in the last 6 months. This is hard to believe, and we are already building parts for the second launch.
Second launch is already being built.
So we have two main processes here. We have manual layup, like you see the colleagues over there. And this is already a serial production, so when they're finished with this bulkhead, they're gonna proceed with the next bulkhead. We're running in multiple shifts right now to have the output we are expecting. And you probably like it more, and I see it moving. This is my top 3 processes where I can have a meditation on. Is the pipe bending, the AM, additive manufacturing,
Yep.
and the carbon fiber winding.
Oh, look at that. It's moving right now, isn't it?
Yeah, and it does it all day long. There's a second machine next to it. We just removed the part and it went into the autoclave.
I've always wanted to see this. I've actually never seen one of these machines working, and it's beautiful. I mean, it is like that's a work of art. It's amazing. And it's almost looks like, from the outside, it looks like a COPV, a composite overwrap pressure vessel, but it's only composite.
It's like only composite in this case. Yeah. No liner inside. There are many things you have to figure out that it works, but when it works and you have an automated machine, you're quite happy.
Yeah. This looks like it's a more or less finished section here, huh?
Yep.
Oh, yes. Look at that. How thick is the end thickness of this thing? Is not
there's
thick.
the precise answer is as thick as it has to be. Different thicknesses because you don't have the same force in all the areas.
Right.
And you don't want to have overweight.
Right.
In your rocket.
Look at that. That's amazing. So once it's laid up, it's going to be laid up over there.
Yeah.
How do you even get that off of there and over to here? Like, what's...
So after you wind it, you take it off the machine. There are certain processes, cutback processes we cannot show today and we wouldn't show. But then you take it off, you move it to, you put a vacuum bag around it. Mm-hmm. You put it in the autoclave, you cure it, and from then on you mill it and you put the bulkheads in.
And all the features.
All the features. And then you see it becoming a rocket.
Yeah.
And that's what we're going to see soon in the launcher assembly.
Cool.
So while RFA was focusing on lowering the cost, ISAR seems to be focusing on performance and the scale of manufacturing. But now let's hop back to RFA and take a look at their Helix engine, where we can see some of their unique production philosophies go another step further.
Super cool. This is the holy grail of Rocket Factory. This is where we make Helix motors.
So what's the main combustion chamber's pressure?
It's 100 bar in this very early version. Of course, we want to take this entire Helix engine up to approach much higher chamber pressures in the future. We want to push it all the way to 300 bar, but now we have very little time. The first design is limited to 100 bar chamber pressure. We want to get into orbit now as quickly as possible. With 100 bar, we have heaps of margin everywhere.
Right.
And with 100 bar, it's simple enough to get to orbit quickly. Remember, there's 100 companies who are trying to do this. We will die if we don't go into orbit now as quickly as somehow possible. And this is right now the time where we fix the engine performance and configuration, and we move on to this first flight as aggressively as we somehow can. If you push this chamber pressure from 100 bar up to 300, the engine doesn't actually grow in size. It stays the same thing. And you can see this is why the RFA 1 launch vehicle can basically grow twice in length. This is the key, right?
Yeah.
Every time the propulsion engineers pull out more performance, more thrust or more ISP,
You can literally grow the rocket.
we can just grow the rocket and we increase payload and the price per payload reduces. And hopefully we get paid at the end of that. Hopefully we get paid at the end of the day and we can survive. The key here is this, all of this is automotive. The company that makes all these inlet lines and all these bellows, they make exhaust systems for expensive cars, and it's the same thing. Like if you buy an expensive German car, the exhaust system company is exactly the same company that makes all the stainless propellant lines also on the vehicle. It's all the
No
same,
way.
dirt cheap. This bellows you find in compensators all the way after the collectors, before the catalytic converters on the car.
So does that mean that do they have to do anything different when it's cryogenic temperatures? Because you'd think almost the
Absolutely.
exhaust
So
would
this
be
is-
the opposite end of the scale, you know?
Yeah, absolutely. So this is where the core IP of us is. We basically use all these automotive companies and components, but the reality is that it's not one-to-one the same thing. We change material specs, heat treatments, welding specifications, acceptance testing methods. All of that IP we roll in, and for the manufacturers, they love it because they can charge us twice the price and they think they're making a killing. Little do they know that we save a factor of 10 compared to the old school aerospace part that is custom made by some aerospace company.
Right.
So
Yeah.
then this is a TVC actuator here, correct?
Yeah, it's a TVC actuator, and the actual brushless DC motor in here is the same motor that you will find in a lot of electric scooters in the future. It's the same thing, it's already built in quite large numbers. The same with this ball screw. This ball screw here is from an industrial application. They build tons of them. Of course, the internals are slightly different for us. Again, same principle. It's a little bit more expensive for them to make us this customized variant, but for us, it's 1/10 of the cost compared to going to a dedicated specific space company. The gimbal is a really cool example. It's straight out of a race car. It's literally nothing different. You could design the gimbal yourself from scratch and make it expensive, but this is only a couple of $100, and it's straight out of an automotive application, straight out of a race car. The same with a lot of the valves. We actually went to a lot of these German automotive companies and we asked them, look, what are the most reliable sensors and the most reliable valves that you guys use in your cars? And they told us, look, they're actually not in the car. The most reliable valves that we have run all the spot welding guns in the manufacturing line. Because if that fails, we lose millions of dollars every hour of this manufacturing line standing still. And that is the valve we have chosen, and we basically said, look, we're going to use this valve everywhere. And this is like a standard valve, and the engineers didn't have a choice to go and get something custom. We basically said, this is a valve. We will talk to the manufacturer to make it bulletproof, increase the pressure rating to 400 bar, and then we just use it everywhere. And we have hundreds of these valves on the vehicle, on the engine. It's always the same thing.
And have they been in testing so far? Have they been reliable and up to your standard? And
they were the most reliable valves. They are the most reliable piece of equipment that we have on the entire vehicle. And the key comes from, obviously, this valve is built in thousands of, in very large numbers, thousands every year. And again, it's not exactly the same as the valve that you will find on a manufacturing line at these automotive companies. It's slightly adjusted. We have different seals, we have slightly different parameters in it. The key is it's not from a dedicated space supplier that charges you 5-10 grand per valve. This costs a few $100s per valve.
So your biggest worry is not about maximizing the, going down to the gram for every single component and trying to minimize the mass of the vehicle. You're really looking at every single thing as what is the cheapest way to get to orbit.
Yeah, absolutely. For us to be competitive, there's only one thing, and that's the payload cost to the customer. And it's all cost-based. We have a mass model, but the mass model is not super stringent. It allows us to basically spin in all these automotive solutions. And literally, we are a bunch of automotive guys that build a rocket rather than a rocket company building a rocket. You're probably familiar with these connectors. You will find them on every
Isn't that an OBD,
ECU.
OBD2 port?
Very similar. You will find these on the ECUs of cars, and some of them run airbag signals. So how reliable are they? Super reliable.
Yeah, they have to be. Yeah.
So as long as they use the right material without a lot of water in it, we can use them in vacuum, and then they're good to be used here. The key is that they've built millions and millions. We build about 10 million motor vehicles a year. Right? That's a lot of experience, and you have to tap in there. If you don't tap in there, you're making a mistake. This is what we're all about. We use automotive to the core. Every single component we ask, how would this look like in automotive, and how much does it cost in automotive? And we always find not small differences, we find orders of magnitudes of differences in cost. And that's what the key here is, to make it really low cost for the customer.
So actually engrave even your initials here.
No way. My initials are gonna go to space, baby.
Yeah, for sure.
This engine better not blow up.
Well, it's his responsibility now.
Yeah, that's awesome.
Alrighty, so
Alright.
you're gonna, I hand you, let's do it like this. You get these fasteners because I need to get one
Yep.
quick in.
Yep.
Otherwise it falls down. I hold it for you, you just flick
Cool.
the first one in. Just goes right here, so we put this here.
What is this, about an M8 bolt?
Oh, it's M6, yes.
M6. Is the flight computer custom made or is that?
Unfortunately, the box is, it really hurts me because I wanted to use a cheap box that costs $5, but we decided to CNC machine it, and I hate it. Looking at it, it knows that there's some money missing in the company because we decided to CNC machine a box. It should be some.
You probably need the one or the other part which looks really aerospace, so you can save this engine.
Yeah.
Hey, I mean, at the end of the day, it's at least beautiful, right?
It is beautiful. At least what you will find on the inside is really low cost.
So it really does just absolutely bug you to the core when it's
CNC machine. If I see a CNC machine part, I know, okay, I want this for my own projects in my own garage. But when I see it here in the company, I'm like, that's just way too expensive.
Then you have this nice bracket, right? Which is like nicely just laser cut, two-dimensional, and just weld together. So
Yeah.
that's what we do.
The
a lot,
key
as you
here,
can see.
the key, if you look into automotive, why they can make cars so cheap, it's because the entire car is based on sheet metal. Everything is sheet metal, right?
Right.
They don't CNC machine much.
Right.
And this is why sheet metal is the key answer. Every design that you see here, I always ask the engineers, look, show me the sheet metal version. The sheet metal version is king. I mean, that is
Right.
cheap and that's king. And if you use the right material, it can be equally as good as some CNC machine part.
Before you
So RFA wants to buy as much from other companies whenever possible. But this is very different from what ISAR's VP of Launch Vehicles, Marco Steamer, said to me before our tour.
So we always look into how can we have maximum control over everything? How can we have the most understanding? How can we have everything as vertical as we can in-house? Because we are convinced this is what makes us the fastest, in the end also the most cost-effective in developing and in the end operating our systems.
So ISAR is focusing on vertical integration, scalability, and as much full automation in production as possible, which they say will enable them to build many rockets cost competitively. And this was pretty evident when Bjorn showed me their 3D printers.
Wow, so just tiny bit by tiny bit. Is this the thrust chamber itself that's being printed here, or what are we actually looking at?
Yeah.
So cool.
What
how
you
fast
also
it works.
see here is on the side you see the small pieces. They are now welded. It's a welding process in the end of the day. And these are for our quality controls. So we tear them apart. We want to get the most out of the material, like all the companies do. But we have it with every single part. We have the test parts where we double check how we can enhance the material specifications. And while we are watching this, there's a thermal camera watching this to ensure that there are no sectors where we overheat the material, because that would weaken our product in the end of the day. Yeah?
So it's always watching, confirming, making sure that everything's good.
And in case we figure out that we are not satisfied with material specifications, we could like rewind on the cameras
Right.
and really see what happened in this exact moment.
Wow.
We're very happy about this, and this is at the moment the latest technology in this field. The printer manufacturer is close by. We are kind of a customer where they usually ask if we want to introduce new technology, so we're checking this. But this gives us a competitive advantage, of course, to be very fast and very predictable in what we're doing.
And again, vertical integration was seen with their engine computers and wiring harnesses too.
Everything built in-house, layups, hardware, housings, testing, This is a very unique approach to have this depth of vertical integration.
Right.
But in the end of the day, first it's a huge hustle because you start at zero. But then in the end of the day, I mean, you can ask the colleague who built it.
Right.
And then you can figure out how to improve it very quickly.
Yep.
You don't have to read wiring diagrams from a supplier. You don't have to get them on the phone when they don't have the opening hours and this kind of stuff. So.
Yep.
Okay, so now let's go check out one of ISAR's early development engines with Marco, where I learned a few surprising facts.
Let's go through our engine assembly real quick
Yes.
and have a look at that. So this is one of our sea-level engines that we use in the first stage. 9 of them in total.
Cool. Look at even the. Okay, so I already have questions.
Yes. Shoot.
Okay, so this is our gas generator here, correct?
That's the turbine.
The turbine, right?
Basically, this
that's
part
separate.
here,
Yeah.
that's the gas generator that feeds hot gas here into the turbine,
And then it
which
spins
is
down.
that big part, and goes through the exhaust.
Yep.
So it's an open cycle. We don't feed it back into the main chamber.
Right.
It goes through the exhaust, and then this turbine powers the two pumps that sit on a shaft upstream.
And
So basically, this is the liquid oxygen that comes in here from the top and goes out here, and then the lower one is the propane.
liquid propane. And the I'm curious why why we have a little like de Lavelle nozzle thing in the turbine exhaust. What's that for?
This is purely for performance, so we can get a slightly higher ISP also from the exhaust stream.
Because it helps speed up the exhaust velocity, or
Yeah,
what?
exactly.
Huh.
It's a small nozzle.
That's that's crazy. I don't know why that surprises me. I'm surprised there's enough pressure. So does it actually get supersonic here then at the end of it? So it actually chokes the flow and goes supersonic.
Yeah.
And so it even would contribute a small amount of thrust, I assume.
Yeah, you don't want to waste any of that propellant.
Right. That's pretty spectacular. Okay, so you said the oxygen comes in on the top here.
Yeah.
So oxygen, I better make sure I'm pointing. So oxygen comes at the top, goes through the pump here, and goes over here to the
So this is the main valve.
main oxygen valve.
Main oxygen valve assembly.
Yep. Which then, wait. Why is your main oxygen assembly valve go into the? Oh, it goes right into the. Hang on. It goes right into the. This is the manifold for the bottom of the chamber.
That's the manifold, exactly.
Are you cooling half of your chamber with oxygen?
It looks like it. And basically, from there it goes through the chamber walls into the injector head, which is up here.
So you're using liquid oxygen through the regen channels.
Yes, we do.
That's cool. I've only heard of one other engine doing that, and it's the dual expander cycle engine. I think it's the BE7 does both, and there's a Russian engine that did that too.
Yes.
And I've always wondered why not, because it just seems like it actually makes a lot of sense, you know. And obviously the risk is if you have a leak somewhere, hot gaseous oxygen leak equals bad, but just don't have a leak.
Exactly, but that's a simple just don't have a leak. It's simple to say.
Yeah.
So yes, I think people are afraid of touching the topic because hot oxygen, that's just going to burn with anything you give it.
Right.
So you need to really control that very, very well.
Yeah.
But in the end, oxygen can give you a lot of cooling power
Yeah.
that you can really benefit from.
Okay, that's awesome. So let me follow the fuel and see if we can figure out follow the fuel and see what the fuel's doing. So the fuel.
Exactly. So this is the propane pump. So we'll have to go to this side here
Oh yeah, just that little guy there.
to follow the propane flow into the main valve.
So main fuel valve down here, and this is the coming in there, main fuel valve, and then the main fuel valve mostly looks like it's going through the regen channel, down the nozzle, back up the nozzle. At what point does it go into the gas generator?
There you go, out of the nozzle
Yep.
and up into the injector.
Yep.
And for the gas generator, we tap off the propellants directly from the main valve, so you don't have
right.
this line connected right now.
Yep.
But it goes, basically the main valve assembly consists of several valves that control the entire cycle.
Right.
So you see one line being attached here, that is certainly the propane line.
Oh, right. Yep. Yep. So yeah, so the propane line runs, that's gonna go back from that main fuel valve area, right?
Exactly.
And then run from here down, and that's how it's getting into this pre-burner, which of course, or the gas generator, which of course the gas generator is basically just a fuel-rich, basically a fuel-rich small rocket engine itself.
Exactly. So you burn it fuel-rich, so the gas doesn't get too hot.
Yep.
Because we don't have regen cooling of the gas generator, and especially the turbine blades cannot see that much temperature, because definitely don't want to have regen cooling of turbine blades.
Right.
That's why you go fuel-rich to just burn colder. It's not as efficient as having a perfect combustion, but it's good enough for the bypass.
You're getting as much energy out of it as you can while keeping it at a sustainable, maintainable temperature.
Exactly.
How do you spin start this engine then? What's the spin start mechanism?
It's pressure fed spin start.
Okay, and
It's
just
very
nitrogen or
Helium.
Okay. And so in spin start, do you actually just literally flow it through the gas generator and like that, or is it a separate, like spin start?
No, the
kick
spin
port or something.
There's a dedicated port for the kickstart, which.
In fact, is it this going down meets into here? This line, because it has its own tap off over here.
You know our engine better than I do. This is the spin start.
Okay.
Yeah.
That is so. I love the compact turbo machinery. I mean, it just reminds me of, I've seen turbochargers on cars.
Yeah.
About this size. So to see this powering a rocket engine capable of how many?
Yeah, this has the power of multiple cars, right?
Oh, like 100 cars basically.
Yes.
Which I think people just don't understand the amount of energy that gets unleashed in something even this size is phenomenal. Yeah. And then do you guys? I mean, like things like this gimbal mount here. Mm-hmm. I mean, do you guys manufacture that in house, or is that?
Sure.
Yeah.
That's also manufactured in-house. That was actually one of the very early test rigs that we had built, was for the gimbal to do the structural testing and to actually swivel the engine around. All in-house built. Basically needs to bear the whole thrust load and transmit that into that thrust structure.
Yes.
So very highly loaded part. But what you see on this engine is pretty much all of that is designed and built in-house. And especially when it comes to propulsion, we want to keep that technology in-house as much as we can.
Wow.
Back to RFA. We're going to check out their Flight 1 first stage, which was undergoing pre-flight qualification testing.
All right, where are we?
Okay, so this is our test facility. We're just acceptance testing the first stage. You can probably see it through the trees. Let's walk over. This is our secret location. It's actually, we're in Augsburg. We're actually not somewhere on the outskirts. And this is where we have done the largest cryogenic burst test that Germany has ever done. You probably remember this from some of the videos, but we had the same setup last year here, and we went all the way up to the point where it all failed with liquid nitrogen. Now this time around, this is the flight article for the first flight, and we can't kill it. It needs to survive. This is an acceptance test now, so a little bit lower loads, but the loads are still higher than what it will see in flight.
Right.
And this is key now. There's like two main tests. One is just a pressure test, and the second test is basically the drain test. We basically tell the press system to start pressing the tanks, and then we will measure all the mass flows of both basically propellants coming out of the stage tanks, and we need to verify that it's enough so that we can operate our engines and switch them on properly.
All right, so how do you guys ship this, and where's your launch pad again?
Yeah, we are launching from the north of the UK, from Scotland.
That's right.
Saxeford.
Yep.
And the cool thing is that we basically just put this thing on a truck, and the truck itself goes on ferry 123, and then we're there.
So, and where's the port that it goes to? Do you go up to like Hamburg or something?
Yeah. This thing basically travels through Germany on a truck. Germany is a small country, takes you like 7 hours, and you're basically from Augsburg all the way in Hamburg, and then it goes on to the first ferry, a second and third ferry, and then within a couple of days you're there.
But this can fit inside a fairly normal, like on the road container.
Yeah.
Okay.
If you look at the SpaceX diameter, that's sort of the largest diameter you can basically put on the road in the US. It's sort of similar here. We're smaller than that. We are 2 meters, so all the transportation is straightforward. There's no special requirements for it. And yeah, there's not a big deal to ship this to Saxaford.
Will you ship it inside of like a container, or is it just shipped like?
No, it's stainless steel, man. It's like it can be open. It's ductile. We will make sure that it's covered somewhat.
Right.
But we will not put massive precautions into shipping this thing. I mean, it needs to be low cost in every single operation that we do.
And is it slightly pressurized while shipping too? Do you maintain some pressure during shipment?
We can, yeah. So when the vehicle grows, when we increase chamber pressure, at some point we have to put in a small amount of pressure. But this very first vehicle, which we call minimum viable product, MVP, the first prototype, we don't actually need any pressure inside. But as the vehicle grows, at some point we have to put 0.1, 0.2 bars in.
And then that interstage, that's the carbon fiber?
That's carbon fiber, because that's very interesting. The Optimizer never chose stainless for the interstages, because the interstages are not internally pressurized.
Right.
And that means like the best cost to benefit ratio you get if you use a really low density, high strength material. But what it has done is it has always chosen automotive composite. So this is not a space composite. It costs about half than the space grade, high performance, high modular composite. We use a material that is very cheap. It's half the cost. And again, we didn't want to do that, but the optimizer told us, look, it's the best way to make it cost efficient for the customer to use automotive grade composites.
Next, we took a lift up to get a closer look at the rocket and its interstage.
You can see the intermediate bulkhead. Can you see this? Can you see these two weld seams that are close to each other? This is basically, we've been in the first stage earlier today, and this is the second one. Is basically the one where the bulkhead is located internally. Okay.
Yeah, so this is what we were seeing on the ground.
Yeah.
And when we were in it before, I forgot, did it even have a bulkhead in it, or were we at the bulkhead?
We were at the bulkhead. We were exactly at this point. So we were basically in this area of the stage. And you can see some of these welds here that look a little bit funny in color. These are basically locations where we have to re-weld and close the tank to be absolutely 100% leak tight. This is still an ongoing process, but we're getting quite good at it. So let's go up now and have a look into the interstage. See, this interface is super critical, because basically the composite is perfectly in diameter, but the stages are all different. So can you see these flexible fingers?
Yep.
These flexible fingers basically allow us to adopt the accurate interstage to any diameter tank. And once we're adopted, then we weld it on.
Right.
So it's basically reverse. What you typically do in engineering, you weld and then you rivet and then you're done. We do it the opposite way around. We put everything on its head here. We rivet first, then we put it on, then we weld it.
How do you ensure that the interstage is going to be aligned, like left, right on the axes? How do you know it's going to be like perfectly aligned?
Yeah, we basically take 3 spots around the circumference and accurately measure length all the way from the bottom to all the way to the top. And then you have 3 points, and you can really accurately measure it out and basically only start welding and tacking it on if the alignment is perfect.
Right.
The best thing is that we don't need this to be super accurate. As we had this conversation this morning, if the entire concentricity is within 1 inch, good enough. And that's the key to make this cost efficient. And we can make these stages really everywhere. It doesn't need to be a super advanced factory. We can make these in literally any sort of place that knows how to do industrial stuff. And now you get to have a look into the interstage. And this is basically where the second stage nozzle and the second stage engine is housed in during the ascent. So the second stage flange is right onto here. And this composite interstage is something very interesting. Can you see the carbon structure? Can you see the rib structure?
Yep.
Yeah, that's something super special that makes this interstage indeed very lightweight and very performant.
Lastly, let's go back to ISAR and see their fairings and flight hardware to get a sense of what their vehicle will look like when it's completed.
So this is the payload fairing. You can actually hear it. I can hear the echo in the payload fairing. So there's already a few things that I'm seeing, like you got the little COPV bottles, and those, through those, the lines, the steel lines, are what actually pop open all the little pneumatic actuator things.
Exactly. So what you see here along the split lines, also here on the bottom, that's our genetic separation locks.
Oh, right. Because this has to hold on to the payload adapter or the upper stages, hold on to the upper stage, basically, right?
Exactly. So, and this is really just purely pneumatic. There is no pyrotechnics involved. We can test it, check it out as much as we want to before flight. And then it's super reliable, super low shock in flight. So this is the horizontal separation that splits the fairing from the upper stage, and then we have the vertical split line, and then we just have very simple gas spring pushers that will basically push the two fairing halves apart.
That makes sense. So these are these the vents then that?
Exactly.
Sorry, I'm making sure that I can see it on my own camera. So these are the vents that help regulate how quickly it depressurizes, right?
Mainly, if you look further down there, you see a big interface which is for our air conditioning.
Oh.
So while we are sitting on the pad, or even during rollout or during AAT, when we have the payload integrated already and encapsulated, we need to constantly make sure that the right conditions are basically provided on the fairing.
Exactly.
So the right temperature, the right humidity, and that comes through that air conditioning interface, and these are the vent ports to vent out the air again.
Oh, to vent out the air again.
Exactly.
Does it work at all in ascent though? Because I know you don't want to depressurize the payload fairing at the same speed as, on ascent you don't want it to totally depressurize too quickly. How do you regulate that? Or does it not matter?
It's pretty much a passive system. So you just depressurize the fairing as you fly through the atmosphere and the pressure decreases outside, you vent the fairing.
Huh.
It's a very simple passive system. But the AC is actually quite challenging because we want to launch from northern Norway where it gets really, really cold. We want to launch from French Guiana, which is tropical, very high humidity, very high temperatures. We need to be able to deal with all of that with the same system, basically. And especially humidity, that is hard to get rid of, and you need a lot of ventilation. And this whole structure, like one of those half shells, as we said, you can lift that with 2 people and carry it around the entire production. I've done that. It's super light. It's a composite sandwich structure.
Yep, with like aluminum honeycomb or something then? Yep.
And then, of course, you need a heat protection on top, which is normal when you have carbon composite, because especially that part of the rocket gets really hot when you have basically supersonic, hypersonic speeds and you compress the air in front, it gets really, really hot.
Yeah.
So you also need the heat protection there, which protects the carbon composite. What you see here, I think you can guess what it is. This is our
payload fairing adapter, or payload adapter, or whatever you want to say.
That's the payload adapter. So it's actually a standard EELV interface, which you would know from also the US launchers.
And Kerbal Space Program.
Exactly. And this is where the payload fairing attaches to as well. And the payload will sit right on top, of course, with all kinds of adapters you can imagine on top of that. Super light. If you want, we can lift it.
Is the cork here, is that just to prevent like scuffing of because this actually bolts into the inside of the top of the second stage, right?
This is actually the skin. And the cork is basically heat protection.
This is actually on the outside.
Yes.
Oh, that's crazy. Yeah, I would love to lift it though. I would take your invite on Can I?
Go ahead. It's flight hardware. Don't destroy it.
Oh my gosh. That's actually pretty crazy that the entire thing. Yeah, that's pretty nuts. Dang. So this is all on the outside. So these are the hinges then for the for where the fairing attaches, right?
Exactly. This is where the fairing attaches. This is basically where the separation locks will engage,
Yep.
and then they will swing open.
That's really
Also
cool.
a composite sandwich structure, super light, super stiff, exactly the right thing for a payload fairing. Right, then we can move to the interstage. So this sits on top of our first stage oxygen tank. And basically we're right now looking towards the interface to the second stage. So this is where the separation system will be attached. It's actually exactly the same system that we use in the payload fairing.
Cool.
So the same pneumatic locks, the very same mechanism, slightly different and adapted pushers.
Which maybe a little bigger, since it has more mass to push.
To push the stages apart, but essentially the very same system that we therefore also can completely test and check out before we fly, make sure it works properly, and don't use pyrotechnics that are one-off and you never know if it's gonna work in the end or not.
And this allows you to then, you'll get double the test time, I mean, everything is doubled up, so.
Absolutely. The moment we tested this fairing, we had a big foam pit here in the hall and we made it separate in front of the foam pit. We knew the separation system works and it will work here as well.
Right.
What you see over there on the blue table is the assembly of our thrust structure on the first stage, where the 9 engines are being attached. This is the second one. We can check out the structural testing area now, where we have a fully assembled one already.
Oh, awesome. Let's do that.
All right, so this is our multi-purpose structural test rig, which we use for all kind of structural testing of our primary structures. You see the massive hydraulic cylinders here.
Oh, jeez.
That we use to actuate and to create all the load cases that we would have in flight. So we can compress the structures, we can bend them. We also have a tarp to really pull, for example, on the fairing, to really create all the flight loads that we would encounter. And what you see rigged up right here is the aft section of our first stage. So this is the thrust structure that you can actually see the interface points where the 9 engines will be attached to, and how the whole load is then transferred into the carbon composite skin.
Right, through those trellis frame looking things and up into the skin there.
Right now, of course, it's completely wired up with strain gaugers and measurement. All those cables will not fly. But this is the test setup to really accept that thrust structure for our first flight.
So just to confirm, obviously, the carbon composite ring that we see is just there for the testing stand, basically. It's not...
Exactly, that's kind of a dummy structure.
Yep.
In real life, this will be attached to the first stage propane tank.
Yep.
We saw that cylinder in the carbon manufacturing.
Yep.
That's what will be attached to, and then you're gonna have a separate structure, basically a heat shield that protects the entire area from any, flow separation induced hot gas
going back up,
going upwards and burning some sensitive stuff on the structure.
And so all the cables we see now are basically each attached to different strain gauges.
Exactly.
So there's no flight hardware on this. It's literally this entire bundle, snake of cables, is all just to feed data back to your computers to let it know how it's handling these loads.
Exactly. That's all test instrumentation. Only the structures that you see are flight hardware. And those structures where it is actually attached to the rig, this is our hold down release interface.
Okay.
So this is where actually the hold down release mechanism, the clamps will engage in.
Cool.
And where basically the entire 70 tons of thrust will have to be withstood while we sit on the pad until we release.
Yep. So both companies are taking wildly different approaches to how to be competitive. So let's hear in their own words, how do they plan to thrive in this competitive market?
Very cool jumper, Keegan. I love this. Look, this is the #1 country when it comes to space. They're flying into space hundreds of times every year. Europe is flying to orbit a handful of times this year. It's really devastating.
Well, and how do you guys plan to change that?
We build rockets just like cars,
and we're just going to undercut anyone on price.
If I may add one thing about how do we want to compete, it's not purely scalability and automation, it is the level of autonomy and vertical integration that we have. We are extremely flexible and agile in the way we can work as a company. So, for example, if we have an engine on our test site, we build up ourselves, we operate it ourselves. We know it perfectly inside out. We get the test results, we have all the design tools written in-house ourselves. We can adapt immediately whatever learnings we have in the testing. We can adapt the design, we can throw it to production. We need 1 week to produce an engine.
Wow.
And then we can send it up to our test site again and go test the next iteration. That's the core strength of our company.
And in my opinion, this will be a very interesting experiment to see where these companies will be in 10 years, considering just how differently they're taking on this challenge. But I don't think there's any particular key to success here. I don't think there's any one thing that a company can do to ensure they'll be the next top rocket company. Europe is inherently at a small disadvantage by not having any eastern coastlines, and its fairly northern latitudes that all make it more challenging from a performance standpoint. But Europe is also a hub for some of the finest engineering, some of the most high-tech manufacturing lines, and some of the highest educated population in the world. And just like all things spaceflight, nothing is guaranteed, nothing is certain, but it's the fine margins that make the difference. And with some of the smartest minds in the world working to solve such complex issues, chasing those nines, so to speak, I have no doubt some beautiful combination of the right design, risk, investment, engineering, and talented hardworking personnel will help build the rockets of our future. Be sure and follow both RFA and ISAR on their social media accounts to keep up with all their action. I can't wait to cheer them on as their rockets get ready for their first flights. And if working for one of these companies is of interest to you, don't hesitate to check out their career pages to see available positions. Now, they didn't tell me to say this, but I feel like it'd just be a no-brainer. Both companies were awesome, and it'd be so fun to work for them, in my opinion. And as always, I owe a huge thank you to my Patreon supporters, YouTube members, and ex-subscribers for helping make videos like this possible. If you want to support the work I do, head on over to patreon.com/everydayastronaut, or hit the join button on YouTube, or just leave a comment, like, and share to show your support. That's going to do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.